All right, Cass. Back to chapter 11, grounding. Uh, Page 157 says code alert. Unspliced main bonding jumper. Section 250.28. An unspliced main bonding jumper connects equipment ground conductor and service disconnect enclosures to grounding conductor within enclosure for service disconnect. So, main bonding jumper connects my neutral and my grounding bar. Permitted connections. Section 250.8 connects by the exothermic weld, listed pressure connectors, listed clamps, or other listed means. So when you're using something like this, it's your connections can't be under a screw. So they always call it the irreversible connection. So it's a clamp that clamps around, and the only way you can take it off is by cutting it off. Tomorrow I'll try to find one to see if I have one left over. So they're usually called C clamps, and it's a C, and you use your crimper, and then you just crimp it on. So there's no way to take it off. The only way you can take it off is prying it open, try to pry it open, or cut the wire open. Okay, so they're trying to make a straight connection where it's not going to come loose, or somebody manually loosening the screw. It says, due to the high currents available on the supply side of the service equipment, the bonding jumpers must be the same size or larger than the grounding electrode conductor. Section 250.28D discusses bonding jumper size in detail. If a bonding jumper is impractical, other means of bonding such as grounding wedges, grounding bushings, or ground clamps is used. I'll try to find some of those tomorrow. System grounding. So it says system grounding. One circuit conductor of each circuit connects to the ground. Limits voltage. So it says system grounding is a circuit conductor of each circuit connected to the ground. This connection is made at the service entrance equipment. The ground conductors are connected to the neutral bus bar, which is connected to the main bonding jumper, to the grounding bus bar, and a grounding electrical conductor is connected to the grounding bus bar. So going back to this picture here, we got it coming in from the service, coming to the neutral, got the bonding jumper, going to the grounding, and then we have a grounding going to the grounding electrode. Okay, we have one that's bonded to the metal frame. Then we also have another one that's running, so there would be a grounding bushing on maybe on the pipe where that runs it in. In a lot of areas, is if you have multiple entrances into your panel, they want each conduit, especially if they're a concentric knockout, they want a grounding bushing on each one, and that's a bushing you put on and you connect the wire onto it that I passed around a few times. It says the grounding circuit conductor serves to limit the voltage at which the system operates. Further, this ground resists the amount of voltage imposed on the system by accidental shorts between conductor and lightning strikes. The ground circuit conductor can be a neutral conductor or on the face conductor, depending on the wiring systems being used. In addition, information on the system's grounding is found in Part 2, Article 250 of the Code. It says the electrical system's grounding is made continuous from the supply transformer to the service equipment. The following connections, which illustrate, is the figure of 11.5 accomplishes the grounding. It says at the service equipment, the neutral conductor is grounded in accordance with Section 250.24 by connecting with a grounding electrode. So the grounded circuit conductors, a single phase 2 wire. So you have a neutral, single phase 3 wire. You have a neutral, grounded wire, single phase 2 wire. It's only a hot and a neutral. It's only a hot and a neutral. Single phase 2 wire is a hot and a neutral. That's why it's not called That's why it's not called a neutral. That's why it's called a grounded circuit conductor. Now, single phase 3-wire, now you have 2 hots and a neutral, because that's going to carry the unbalance between the two. Multiple phase with 1 wire common to all phases. Common conductor, so that's more on the DC side. Multi-phase, 1 phase grounded. 1 phase conductor. Multi-phase with 1 phase as a single phase 3-wire system. So if you're pulling 3 circuits across, you're only using 2 of the 3. Okay, now it's called a neutral conductor because it's carrying current, because it's an unbalanced load. We talked about that. When is a neutral a neutral? When do you count the neutral as a hot, as a current carrying conductor? So you're using a single phase off a 3-wire system. When you got 3 hots going across with 1 neutral, but you're only using 2 hots with that neutral. Now you got 3 wires in the conduit. So it's a neutral conductor, but it's also a current carrying conductor. So when in a raceway, you have to count it. So here in the picture, they're talking about the system grounding is continuous. Here's your primary side. Here's your secondary side. So they're grounding off the frame. Then here comes our neutral. And neutral comes to the neutral bar. Off the neutral bar, we have the bonding jumper. It goes to the grounding. Off the grounding bus bar, we go to the grounding electrode. Okay, and then it's also got the little dot right there in the corner. And it says bonded to enclosure. So you have to bond the enclosure. Also, everything's got to get bonded. Somehow you got to get and bond that. That says the service interest neutral is connected to the ground supply conductor. Okay, let me go back. At the transformer, we got 3 hots coming in. 1, 2, 3. No ground. And it comes into the transformer. We got a delta coming in. We have a Y going out. Okay, we have to bond, this would be that XO. We have to tie it to the ground. Here they're putting it on the metal frame, and it goes to the ground. That's how we get neutral. There is no neutral. We have to create this neutral, this grounded conductor, and we do it by bonding to the metal frame. Okay, once we have a continuous path all the way down to our panel, to our service, then it runs to our neutral bar. Then we have our main bond jumper that connects our neutral bar and our grounding bar. Then we have to ground the metal frame out, the can, the box, the panel, whatever you want to call it, the meter, all of the above. Then we have the grounding electrode. It says the grounding bar is connected to the grounding electrode conductor, which is connected to the grounding electrode. If more than one electrode is used, they must be bonded together. Also, the grounding bus bar is bonded to the metal enclosure. So again, if you have a second ground rod, say the inspector comes in and says, well, one's not good enough, stick a second one in 6 feet over. You stick that second ground rod in, and you run down and you tie it across. That way they're both tied together. Circuits requiring grounds. Because most circuits require ground, section 250.20 listed the specific types of circuits for which the grounding is mandated. It says for circuits less than 50 volts, grounding is required on the following conditions. The transformer supply voltage and source exceeds 150 volts to ground. The overhead conductors are installed outdoors. The transformer supplied voltage receives the supply from an ungrounded source. So it says transformer supplying the voltage has a source. Okay, so here, if our main power to a transformer, so let's go back to this picture here. So this transformer is exceeds 150 volts, but this transformer is only putting out, say, 48 volts. Then it has to be grounded. Because we're reading, remember, right here, less than 50 volts. Ground is required in the following conditions. So if our primary power exceeds 150 volts to ground, then we have to pull the ground. If the conductors are ran overhead, outdoors, if the overhead conductors are installed outdoors, and then they have to have a ground. The transformer supply of the voltage receives supply from an ungrounded source. An ungrounded source is like over here. That's an ungrounded source. There's no ground coming in. It's just 3 hots. Rarely happens. This is only on the utility side that you see something like this. And then it says AC circuits between 50 volts and 150 volts. I mean, between 50 volts and 1,000 volts. It says for circuits, AC circuits between 50 and 1,000 volts, grounding is required in the following conditions. The system can be grounded so that the maximum voltage, the ground, is not greater than 150 volts. The 3-phase, 4-wire Y system that uses a neutral circuit conductor. So there it is right there. Because they have to ground that transformer out. There has to be a ground. So we're getting the 3-phase with a neutral. Well, the only way you're going to get that neutral is by grounding that center tap of the transformer. Just like they got there. Here is a bond to the frame of the transformer. Here's a ground wire going to the ground. And then here's our neutral wire going out to our service. Okay, the 3-phase 4-wire delta systems that uses the midpoint of a 1-phase winding a circuit conductor. So again, say here, this would be that delta high leg where we're coming off, where it is right here. Here's a picture. A 3-phase 4-wire. So here's circuit A, circuit B, circuit C. And then here's my neutral. Neutral to A is 120. Neutral to C is 120. Neutral to B is 208 volts. So this is a high leg, delta high leg. So this is the one that I always talk about. You have to be careful. That B phase would have that orange tape on it. Okay, that B phase would have that orange tape on it. Ground fault circuit interrupters. A ground fault circuit interrupter is a device designed to open a circuit when a ground fault occurs. The GFI opens a circuit as the current passes through it at the current that is less than the setting of the overcurrent protected device. So again, GFI's trip at 6 milliamps, which is 0.006 amps. The current is above that sufficient to cause injury. Okay, even this here can hurt you. You will feel it. It will hurt before the GFI trips. Okay, so it's like people say, oh, the GFI is protecting me. No, you guess what? You're going to still get hit. And there's a chance that you can still go into defibrillations. Your heart can start going out of whack with that small current. Its sensor to GFI monitors the balance between the hot and the neutral conductor. If a fault occurs, which the current will cause. So on a GFI, let me come up here to my board. If you see the mess on the back side, please excuse it. But I've drawn this on the board many times. Okay, and I send the GFI around. So it has that sensor. Here's my neutral coming in. Here's my hot coming in. Okay, 5 amps. This is my CT, my current transformer inside the GFI. Okay. Current comes in. You got something plugged in here. And then if I got 5 amps here, guess what? I got 5 amps returning on that neutral. Coming through here, because I got 5 here and 5 here, there'd be 0 amps. So this current transformer would be reading 0. The minute this current transformer changes and reads anything, okay, if there's a shift, let's say I got 5 amps here and I got 4.9 amps here. Okay, that is 0.1, which would be 100 milliamps. Remember, if over 50 milliamps, all it takes is to kill you. This GFI would shut off. The GFI would turn off, killing power to the load. Okay, so that's how it works. As long as they're even, the 5 amps and 5 amps, the GFI is working properly. If there's a shift of more than 0.06, which is a lot less than this 100, so this number would be 4.904. That'll give you the 6 milliamps. Okay, so always remember is GFI, that's all the GFI is doing, is monitoring the hot and the neutral, or the hot and the grounded wire, because they should be equal. If there's any change in any of these two, so this one, say, where's that 1 milliamp going? Well, you're down here, and it's going through you down the ground. So you get electrocuted because you just became that light bulb. Okay? So that's how a GFI saves you. Thank you. Bye-bye.